So the next speaker is Arvind Renganathan.
Good morning. Good afternoon, I guess. So today I'll be presenting my work. This is called Knowledge-Guided Machine Learning for Task-Driven Modeling. And it's an approach for few-shot learning in heterogeneous systems. So we call it KGML-TAM for short. So I'm Arvind. I'm a PhD student and professor. Oh, sorry. Can you hear me now? Okay, perfect. I'm Arvind. I'm a PhD student in Professor Vipin Kumar's group. So moving on. So the first thing. So our key motivation is that we have a need to build robust personalized prediction models for a set of entities. So what do I mean by entities here? So we say an entity is anything which has a system which has an external driver acting on it, and it shows response to that particular external driver. So some of the examples could be, we have a streamflow prediction model for data from multiple basins. So in this case, entity would be a thing like basin or a catchment, and your driver in this case is weather, and you're trying to predict something like streamflow. In a similar case, your entity could be something like flux towers, and your drivers could be weather, LAI, and stuff, and your response in this case could be things like GPP, and similar things for, let's say, electrical load forecasting, where you'll have entity as household, driver as weather, and response as electrical load, and so on. So with this in mind, I guess we have seen we have seen a lot of slides so far where we have defined this abstract system, where you have some input going in, and you have some static features or some characteristics of the system which affect and how an output is created. So the basic abstraction we are assuming here is that the system is of that fashion. So with that in mind, a couple of things we wanted to talk about was, let's see this image on the slide. So in this, every row stands for one of these entities. So that means if it's a basin, each of these rows would be a basin for which you have a data for across time. Let's say you're trying to build a model for, let's say, each of those one in green. If you had enough data for each of those greens over time, you could build one model for each of them, and that'll do just fine, but you probably need a lot of data. Let's say you have a reasonable amount of data, then one more thing you could do is you can probably build one model together for all of these greens, and that can help you probably extrapolate that into the future. But what do I do when I have to extrapolate across space? So what do I mean by extrapolating across space? It could be a new entity which you haven't seen during training, or in the flux tower case, it could be a location which you have never trained on. So in those, you have two situations. Either you're trying to extrapolate in space, which is in the same time period as where you have been training. So it could be like historical hindcast or something like that. Or you could be trying to extrapolate both in space and time because you also want focus. A couple of ML approaches you can use for the first scenario could be things like multitask learning, where you just use all of these greens together to predict those same greens for the future. And a couple of approaches for transferring knowledge in the space scenario is zero-shot learning, few-shot learning, and so on. And why is this important? So typical process-based models, you'll have to train parameters for each of them individually. You have to calibrate them. It'll be very hard for you to transfer parameters across. And fortunately for us in machine learning models, you can train them together. So that way, the parameters are learned together, and you're pretty efficient at it. Going on. So with that in mind, let's say our situation was build a model for all the well-observed entities, that is entities on green. ML can leverage all the information across just as we discussed, and but this does need a lot of data if you want to predict in the future. So that's fine. But what if we have a new set of entities for which we have very limited data, which is the few-shot scenario, and that is the rest of the discussion. So that's what I'll be focusing on. If I train a new model just on those limited data I have, I'm probably not going to do that well. It's going to be suboptimal. I don't have enough data to train that model. And I can also train the model on those green without any of the static information and so on. And I can try to apply that model here. That won't work either because, I mean, unless I use the Z to transfer, it's going to be a very generic model, which is not going to have all these processes built in. And it's going to be suboptimal because Z determines what Y output you get. It's not the same. Depending on different Z's, the same X would produce different Y's. So the question is, can we use, let's say you have few shots of information. So can we use these few shots of information in new entities to leverage information from well-observed entities to make a prediction there? So a very common technique used here, or a series of techniques, or let's say a set of techniques used to do this would be something like few-shot learning. There are a class of ML methods which are trained on several related tasks during training so that it can generalize well to unseen tasks with just few examples during testing. But the problem is most few-shot learning methods, which are model agnostic, often are probably based on MAML, which is a gradient-based method. And it often has difficulty. One problem is it's computationally expensive. You'll probably have to calculate Hessian. And even if you have their first order approximations, it has problems with gradient propagation and so on, and it often works only on unity model distributions. But if you move on to other methods which don't have these issues, but the problem is they are built only for image classification and they don't really work for time series aggregation, which is the problem of interest here in this case, or we are trying to build a model agnostic method here. So what can I do? Another way to use these few sets of information in a new entity, especially for these abstract models, or can I use this limited information? Let me try to build an inverse model with this limited information, which will identify the Z for us. The Z could be changing in time, or it could be constant across time. Here we are trying to find constant parameters across time. This could be a parameter estimation task. And what we're saying is, okay, once we find this, then we'll use these parameters along with the parameters of the forward model, which is also trained, together parameterize this whole system to make my overall prediction. So what would it look like? So this is an overall architecture. So I have some inverse model. It's taking inputs and outputs in the past, or whatever few shot data I have. It's creating some parameters, which I call modulation parameters here. And your final forward model is effectively a combination of these modulation parameters and the forward model's parameters itself. And together, these will make my final prediction. So that's just a small caricature there, just so that it's much easier to understand. So the first thing we did is we tested this on, we were trying to predict GPP. So that was the first test case we did. And why do we want to do that? The main reason being high resolution flux, carbon flux data is not really available in tropics or semi-arid regions. And it's really important for us to know that to determine the global carbon cycle and so on, especially in this climate global warming era. So the first test case we had was this FluxNet data set. FluxNet data set is sparsely sampled 200 sites across the world, which have daily, hourly, monthly time series data and so on. In this, we took the regularly sampled daily time series data. So it's a very clean data. We followed a similar strategy to another paper, which was published about a year ago. So they had selected 17 testing sites out of these 200 testing sites, which they say are important because they're mostly in semi-arid regions and every functional type. So what they're trying to say is if you build a good model for these 17 sites and show that they work, so if you use this model to then extrapolate across the world, it'll probably be a good data set. Or probably be a good metric or global carbon measure. So the rest of the 189 sites were used for training, and we just used an ensemble strategy of mean predictions from 5 different rounds, and metric of interest reported, and this would be RMSE. So this is just a couple of results here. The first one, which says local fine tune. So what we've done is just basically don't consider any static features. We just train one particular model across all the training data you have. And after that, you go to your testing sites, and whatever data you do have, you use that to fine tune your model. So the columns are 1 month, 3 months, 12 months of data, and 24 months of data, which was used for fine tuning. The second model is your standard MAML approach. The next one would be a much slightly more advanced version of MAML, which is called multimodal MAML. And as I was just telling earlier, MAML works only on unimodal distribution. So multimodal MAML is actually an extension of that for multimodal distributions. And the last one is our KGML-TAM approach here. And one thing you can probably observe is that as the data, as more and more data we have, the local fine tune works just fine, but unfortunately that's not the reality. So you'll probably have to hit 12 months or 24 months to even hit that extent of information to build a good enough model there. So you probably need one of these MAML multimodal MAML or KGML-TAM. And KGML-TAM can do very, very well, good even with 3 months of data or 12 months of data, where it pretty much beats everything by about 20–30%. So this shows us a promise that it does work. So our next steps are to use this model to create a global data set of GPP across the world. And there already exists a data set of that fashion, which is this Metaflux paper cited right there, but they have used MAML, and we think that the results we are giving would be much more physically consistent, and earlier results and other data sets to verify that do support that. And yeah, we did similar things on Streamflow. We observed the same things. And that ends my talk for today. Thank you. Any questions?
Okay, maybe I have one question. Oh.
Hello.
Yeah,
Yeah,
hello.
I have a very general question on using inverse modeling for like personalized predictions. I mean, what is the high level intuition behind how you would use that?
Okay, how do you use them? So what I'm trying to say is, let's see, maybe I do have a slide for it. Just give me a moment. So let's just take this image. I think Praveen also had it in a slide. Let's just take this image. So let's imagine your process, or maybe this will help. So imagine your process is this X to Y model, where the Z are the personal traits of that particular model. So the Z determines the X to Y transformation. So what I'm trying to say is, if you can determine the Z, you can make a model which has this in it, it's parameterized by it, and overall it'll be able to do this prediction well. So all you have to do is you'll have task specific parameters and you'll have task agnostic parameters. The combination of both overall will give you the total model. Does it make sense? The personalized model. Thanks. Yeah, perfect. Thank you.
All right, because I think, yeah, thank you again for Arvind. Yeah.